In this video, we're going to start switching gears. Up to this point, we have been looking at the derivative, which again, your derivative, the notation we use if y is a function of x, we say y equals f of x, f prime of x, that's your derivative function. It represents your slope of your tangent line if you're talking about the derivative at a point. It represents the slope of your graph at a point. And it also represents your instantaneous rate of change. All of those are synonyms, right? What we've done before was we've defined that the derivative of a function at a point gives the slope of the tangent line and is theoretically the limit of your average rate of change function of a function. And basically the way we said that limit piece was to do the average rate of change over shorter and shorter intervals near the point where you want to find your derivative at. And so we can obtain the derivative function doing a similar calculation, but for any value of x instead of at a specific point, but for any value of x in the domain of your function, where your function and your derivative are defined. And so I have two things here. I have this limiting notation here that gives not only the derivative at a point, so here to the left, we have the derivative at a point, x equals a, right here in this one. And then here, this is our derivative function. This is for any function that has an input value of x, and your function is called y equals f of x, right? Now, this definition follows closely from what we know about average rate of change, right? Remember, when we did average rate of change, we said the average rate of change was f of b minus f of a all over b minus a. And so if I think of a number line, so I'm just going to think of a number line in my xy plane. Let's just think about our xy plane instead of a number line. And so if this is a and b is greater than a, now there's a distance between a and b, right? And so I'm going to call that distance between a and b the variable h. And so instead of using two separate letters for a and b, well, if b is h units from a, then b is the same thing as a plus h. And so I can, instead of writing b right here, I can replace that with a plus h. And so that'll be f of a plus h minus f of a. And since I had a b in my denominator, I can replace it there as well with a plus h. So that is the a plus h minus a. And as you can see, this a and that minus a there cancels. And we basically get this notation here, which we call our difference quotient. And if we want our distance from our interval from A to B to be smaller and smaller and smaller, that means we're going to let this h right here tend to 0. I want h to get smaller and smaller and smaller, meaning that B is going to cause me to have a smaller and smaller interval near A. And that's what this limit thing right here is doing, making our interval smaller. This is what's going on in the background every single time I evaluate my derivative at a point. And this is what is going on every time I find my derivative function for all x where my function is defined and the derivative and this limit actually exists. Okay, and so we can use these formulas to actually find a derivative at points and our derivative functions, but that can be a very hard calculation to do. And so what we're going to do is we're going to focus on some formulas that'll allow us to go around having to calculate these limits here in order for us to find a derivative. So let's talk about some of those formulas here. My first formula is the derivative of a constant function. Remember, your constant function is a function who equals a constant, which equals a constant. An example of a constant function would be something like f of x equals 3. All right, f of x equals 3. All right, this function, if I graph it, is a horizontal line because that's y equals 3. That's the function whose y values are always 3. Well, that makes a horizontal line. So in my xy plane, this function would look like this. That's the line f of x equals 3 or the line y equals 3, y equals f of x, right? And so remember, the derivative is the slope of our tangent line. Well, if I pick any point on this line here, because it is a line, the slope is going to always be the same. And so since it's a horizontal line, we know that the slope of our horizontal lines are 0. So the derivative of a constant function is always 0. If I ask you to find the derivative of f of x equals 3 or 4 or 7 or -5 or -10, then the derivative f prime of x, the derivative function is just f prime of x equals 0 each and every time. All right, the derivative of a linear function. All right, I'm going to do an example of that, right? So I'm going to give an example of a linear function, f of x equals 2x minus 1. All right, so if I were to graph this function, it would be a line, right? It will have a vertical intercept of -1. And if I go up 2 units and to the right 1 unit, I'm going to be on that line. And so I'm just going to try to draw that line, sorry. And I make sure it goes through that point, right? So I want to be a little particular here. And remember, your derivative is your slope of your tangent line. Well, if I pick any of these points on this line, my tangent line is this line because it is a line, right? And so my derivative is going to just be the slope of my tangent line. And since the slope of any line is the actual line, then my derivative is the slope, which equals 2, right? So f prime of x is 2 in this example. And now, if I had any other line, right, the slope is always given by m. And so since my m is what my derivative equals, it's the slope of your tangent line, which is going to be the slope of your line, then the derivative of every single linear function is its slope m. So that's a formula. So now we have the derivative of a constant function is 0. The derivative of a linear function is m. What's the derivative of a power function? Remember we said power functions are functions, this was back in chapter 1. Power functions are functions that can be written in the form f of x equals k times x to the p, where there's a coefficient times x to some power. The power rule for derivatives is that this derivative is going to equal, okay, now I'm taking off this k, and we're going to talk about how the derivative is affected when we have this number multiplied out front. So if I just look at, all right, I'm going to look at this. So in my formula here, we have an n instead of a p, and my power rule says it's going to be n times x to the n minus 1 power. N times x to the n minus 1 power. So what we're doing here is we're basically bringing this original exponent out front and making it the coefficient, and we're reducing the exponent by 1. This is the power rule. This power rule actually comes from doing this limit on a power function, all right? And so that's where this formula comes from. Now, we're not going to talk about limits and all that stuff like that in this class, but that's where this power rule comes from. We're just learning the formulas and recognizing when we can use the formula. And so I have some examples here where we may use one or more of these rules here. For instance, I have find the derivative. I have y equals 7, right? Well, this is y, my output. 7 is my function. It is a constant, right? So this is the derivative of a constant. So I know we can say that y prime, the derivative of that is going to be 0 because the derivative of a constant is 0. Let's go to part B. Y equals x cubed. Oh, this is a power. This is x to a power. So I have to use that power rule right here, right? That power rule says, now I can use y prime or I can use dy dx, right? Because my input variable is x, my output variable sitting on here, one side by itself is y. So I can say dy dx. And my power rule says bring your power out front, which is 3, and reduce your exponent by 1. Well, 3 minus 1 is 2, so the derivative of x cubed is 3x squared. Let's go to part C. I have f of x equals negative 2x plus 5. Notice this is a linear function. This is a linear function. And we know that the derivative of a linear function, f prime, is its slope. And the slope of this function is negative 2, right? And so I've used the derivative of a linear function. Here I have f of x equals the 9th root of x to the 10th. Notice this is actually a power function, but the way that I see it written, it does not look like a power function, right? It's a radical expression, but we can change any radical expression to its equivalent expression by using a fractional exponent. Remember, before I even do the derivative, notice that I said before I do the derivative, I'm going to write this so that I can see one of these rules. I don't see anything with the radical, so I've got to rewrite my radicals, all right? Remember, we keep our base the same. The power of that function goes on the numerator, of that variable goes on the numerator, and the index, what type of root, goes in the denominator, right? So before I even do any calculus, we use our pre-calculus, our algebra knowledge, to rewrite radical expressions so that they are now powers, right? Fractional exponents. And now that I have it written this way, I see that this is a power rule. So I can say f prime of x equals, again, we do the same thing that we did in part B. You bring your exponent out front, and it's now your new coefficient, and you reduce your exponent by 1, right? Well, 10 over 9 minus 1, well, 1 is 9 over 9, so that's 10 over 9 minus 9 over 9. So I get 10 over 9 times x to the 1/9 power. That is what f prime of x equals. All right, we have two more rules that we're going to look at. The next rule is the derivative of a constant times a function, or a constant multiple of a function. Okay, well, this is the derivative. This says do the derivative of c times f of x. Well, it's just c times the derivative of f of x, which is the same thing as c times f prime of x. So basically, if you have a constant multiplied by your function, then when you do your derivative is just going to be that constant multiplied by the derivative using whatever rule you have with you. For instance, in part A here, I have f of x equals 10 times x to the 6th. Well, that 10 is a constant multiplied by x to the 6th, which is a power, right? So when I do my derivative, f prime of x, it's going to be 10 times whatever the derivative of x to the 6th is. Well, x to the 6th is x to a power. So I use my power rule there. So that I bring that 6 out front, and I decrease my exponent by 1. And so I get 6x to the 5th as the derivative of that x to the 6th. And so that's multiplied by 10. And so my overall derivative will be 60x to the 5th. All right. When I look at f of x equals negative 4x over 5. Now, in none of these examples that we just did was the derivative a part of a fraction. Or sorry, our variable a part of a fraction. But remember that when you have something like this, by algebra, you can just write that as 4/5 times x. All right? 4/5 times x. And now you can see that this is actually not anything but a linear function. That's x to the first power. So the derivative of a linear function is its slope, which is negative 4/5. Now, if you didn't want to think of this as a linear function, you could still use the power rule, all right? So alternatively, you could say, oh, well, that's x to the first power. So if I want to do the derivative of that, well, I have my constant multiplied out front, and my exponent will be multiplied out front, and I reduce my exponent by 1. Well, 1 minus 1 is 0, so I get negative 4/5 times 1 is negative 4/5. That'll be x to the 0. And remember, anything to the 0 power except 0 is 1. So that's negative 4/5 times 1, which is negative 4/5. So if you don't want to do the derivative of a linear function, remember, it's just a power rule. You're just using x to the first power. It's the same thing. Let's go to part C. I have f of x equals 5 times the cube root of x. Remember, if I don't see a power rule or a linear function or a constant function, I've got to write it to where it looks like that, right? And so whenever we see these radicals, what we need to do is we need to rewrite them using fractional exponents. And so since my radical is a cube root, that's the same thing as the 1/3 exponent. Now I can use my constant multiple rule to find my derivative. So my derivative is going to have a 5, and I find my derivative of x to the 1/3 using my power rule. And so I get 5 times 1/3 is 5/3, or 5/3, and then 1/3 minus 1 is negative 2/3. So my derivative is 5/3 x to the negative 2/3. All right, let's go to part F. Now, remember, if I don't see it looking like a power rule or anything like that, I've got to get it to look that way, right? So we got to remember our stuff from algebra. So from algebra, when I see a radical, I could write it as, well, I keep my numerator the same, but that's going to be x to the 3/4. My index of that radical, that fourth root, goes as 4 in my denominator, and my numerator is the power on the x under the radical. And remember, none of these rules, let's go back to these rules here. My function was not in the denominator here. My function x to the n was not in the denominator here. It's a linear function, so x is in the denominator here, and that's a constant function. It doesn't even have an input variable. So with this being in the denominator, I cannot take the derivative yet, not with the rules that we know. And so what we're going to have to do is we're going to bring that thing that's in the denominator outside of the denominator by making that exponent negative. So instead of it being a positive 3/4 in our denominator, when we take it out of the denominator or do its reciprocal, we have to negate or do the opposite exponent, and that's the negative 3/4. Now that we've done that, we can find our derivative, f prime of x, excuse me, and that f prime of x is going to have that 10 because our constant multiple rule. I bring that negative 3/4 out front, and I reduce my exponent by 1. Now 10 over 4 is 5/2. Multiply that by negative 3, that's a negative 15 over 2. Or you can say that's negative 30 over 4. Negative 30 divided by 2 is negative 15. 4 divided by 2 is 2. And negative 3/4 minus 1 is negative 7/4. And so I get that as my derivative. We also have a derivative of a sum or a difference. So the derivative of the sum of two functions is the derivative of the first term in that sum plus the derivative of the second term in that sum. And the same thing happens with the subtraction. And basically, it's basically saying if you have a sum or a difference of two functions, then you can take their derivatives separately and do that sum and difference separately. All right. And so if I look at this example here, I have y equals 1/2 x to the 4th minus x cubed over 6 plus 4 over x squared plus 3. I'm going to do these derivatives separately, right? Before I start to do any of these derivatives, I'm going to examine them to see if they're written in a rule, right? This is a constant multiple rule with a power rule here. Here, I want to rewrite this as minus 1/6 x to the 3rd power, right? So I can see my constant multiple and my power rule. Here in this one, my x is in the denominator, my x squared is in the denominator. There is no rule right now that I know that'll allow me to do a derivative with my x in the denominator. So I'm going to bring it outside of the denominator by doing the opposite exponent. And then I have this constant here. Now that I have that, when I do my derivative, I can say y prime or dy dx. And that's going to be a 1/4. Sorry, that's not a fourth. So 1/2 there. But I bring my 4 out front and I reduce my exponent by 1. 4 minus 1 is 3. Minus 1/6. I bring this 3 out front, reduce that exponent by 1. I'm getting 3x squared. My constant multiple, that's 4. Bring that coefficient out, sorry, that exponent out front. Negative 2 minus 1 is actually a negative 3. And then this is a constant function, and the derivative of a constant is 0. Everything else is simplifying. 1/2 of 4 is 2, so that's 2x cubed. 3 over 6 is 1/2, x squared. Positive times a negative is a negative, 8x to the negative 3. That is what my derivative equals. In part B, I have f of x equals ax squared plus bx plus c. The reason why I'm including this example here is because I want you to be aware. In all of these other examples, I've only had one variable on my right-hand side, right? And so it was kind of implicit that my variable on which I'm doing my derivative with respect to is x, or whatever variable was on that side. Here, I have an x, but I also have a, b, and c. Notice I use this notation because I'm letting you know that my function is a function of x. So if I see any other letters or variables that appear in that functional expression, then they are constants. They're like 2. They're like numbers. And so when I do the derivative with those things, I treat them just the same way as I treated that 1/2, that 1/6, that 4, and that 3, right? When it was multiplied by a variable expression, it stayed in my derivative, right? Now, the derivative of x squared is, but this is a constant multiple. That's why I wrote that a. It's going to be a times. I bring that 2 out front and reduce the exponent by 1. I'm not going to write the 1 as the exponent there. The derivative of x squared is 2x. I go to my next term. It's multiplied by a function. So I have a constant multiplied by a function. This function is linear. Or if you want to think of this as a power function, that's 1 times x to the 1 minus 1, which is 0. And then this is a constant. This is a constant term. The derivative of a constant term is 0, right? So I get 2 times a times x plus, well, this is x to the 0. That's 1. And so that's b times 1, so that's b, and that's 0. So I get 2ax plus b. In addition to doing these, now we can evaluate our functions, our derivative at a point. Before, if I asked you to do f prime of 3, you would do f of 3.001 minus f of 3 over 3.001 minus 3, right? Well, we no longer have to do that anymore. What we can do is first find f prime of x, right? To find f prime of x, and I know that f of x equals x cubed, I bring that 3 out front and I reduce my exponent by 1, I get 3x squared. Now, no matter what my input value is, I can plug it in and I can figure out what my derivative equals, right? So that's 3 times 3 squared, that's 9 times 3, which is 27, right? And so when my derivative, my slope of my tangent line at x equals 3 is 27. That means my function is increasing by at 27, right? That means if I increase my input value from 3 to 4 units, I expect my output to go up approximately 27 units. Not only can we evaluate our first derivative, but we can evaluate our second derivative. Remember, the second derivative is the derivative of the first derivative. And since we already know our first derivative here, to find the second derivative, we just take that derivative of that value, right? So the derivative of that is a constant multiple with a power rule. So it's still going to have that 3 in there, but I'm going to have to bring that 2 out front and reduce that exponent by 1. 2 minus 1 is 1. And so our second derivative equals 6x. And so now that I know the function for our second derivative, if I want to find f double prime of 3, then I just plug in 3 for x into my derivative function, and I get 18. And so this tells me that my derivative function is increasing by 18 units of my output divided by my units of my input. All right. This also tells me that my original function is concave up because when the second derivative is positive, the first derivative is increasing and your function is concave up. All right. I can ask questions about that, right? Very quickly now. And then the last thing we're going to talk about is using the derivative formulas to find the equation of the tangent line. We've talked about the tangent line repeatedly throughout the semester. Now we can find the equation, right? In this last example here, I just came up with a quick way to find f prime of 3, right? F prime of 3 is the derivative at x equals 3. And remember, a synonym for the derivative at a point is the slope of the tangent line, right? And so since the slope of the tangent line to the curve is given by the derivative, or f prime evaluated at some value, a, we use differentiation. By the way, differentiation, I didn't even define this, right? This is the process of finding the derivative. That's what we call differentiation. The process of finding the derivative. That's differentiation. And so it says we use differentiation to find the equation of a tangent line, right? Remember, if we want an equation, y equals mx plus b, we need a slope and a point that the tangent line will pass through. Well, the slope is going to be the derivative evaluated at that input value. I literally got stuck just now. And then the point is going to be a, and you can plug that into your function to find your y value. Now, why can you plug in? So we want to find the equation of a tangent line when we're given a function, right? So say we're given a function and we want to find the equation of a tangent line at x equals a. Well, we know that the slope of my tangent line is the derivative at that point. So the slope of this line equals f prime of a. And we know that because by the definition of a tangent line, the tangent line touches your graph at that point, right? So the same, if this, okay, if this is my function y equals f of x, right? Then this point has an ordered pair a, f of a. Not only does this function pass through that point, but because this is a tangent line, the tangent line is that point is also on your tangent line. And so if I want my slope, I'm going to find a derivative of my function evaluated at that input value. And the point that the tangent line passes through is going to have that x coordinate, that same a, and I just plug it into the function, and that gives me my point. And so let's find the equation of a tangent line to the function f of x equals x squared plus 2 at x equals 1. All right. The first thing I'm going to do is I'm going to find the point that my tangent line is going to pass through. The point is a, f of a. My a here is this value where I want you to find your tangent line at, which is 1, right? So that's x equals 1. So f of a equals f of 1. That means I plug it into my original function. I plug in 1, I get 1 squared plus 2, which equals 3. So the point that my tangent line passes through is also the point on my function, is the point 1, 3. Now let's find our slope. Well, the slope comes from evaluating our derivative at a, so I got to find f prime of 1. Well, I know that my function is x squared plus 2, so f prime of x is going to be a 2x plus 0. You bring your 2 out front and reduce your exponent by 1, you get 2x. The derivative of 2 equals 0. So my derivative is 2x. Now I want to evaluate my derivative at x equals 1 because that's my value a. That's where I want my tangent line at. And so I'm going to have 2 times 1, which equals 2. And so I have a point that my line passes through, and I have my slope that my line passes through. I can use y equals mx plus b, and I have all the information I need. My m is 2. My input value is 1. My output value is 3. I can solve this to find my y-intercept. 2 times 1 is 2. If I subtract 2 from both sides, I get b equals 1. So I get the equation y equals 2x plus 1. This is the equation of my tangent line. And so what I'm going to do is I'm going to graph both the function. So my function was f of x equals x squared plus 2. And my tangent line is 2x minus 1. Sorry, 2x plus 1. I want to graph that so that I can see that this is in fact my tangent line, or at least it looks a little similar. And so I'm going to go here. I'm going to go to y equals, and I'm going to put my function, which is x squared plus 2. Press enter. And then I'm going to go and enter my tangent line, which is 2x plus 1. And I'm going to get my standard viewing window. So I went to zoom, and then I chose option 6. So there's my parabola, and there's my tangent line. It's going to touch my graph right at x equals 1. Now it looks like it touches more, but it actually just hits it. My calculator is pixelated, so it's only going to be so precise, but my tangent line is at x equals 1, y equals 2. Y equals 3, sorry. But that is it for this video. So you should know how to take the derivative, knowing how to do the derivative of a constant, a linear function, a power rule, a constant multiple rule, and a sum and difference rule. We're going to add more rules to our next lesson. See you next time.